Okay, hello there everyone. I'm Parker Glynn-Adey. I'm an assistant professor at the University of Toronto, Mississauga, and I want to tell you a little bit about my work on geometry, as mathematics for the eyes and hands. In this presentation, we usually hand out physical objects to play with, and we sort of have a bit of a conversation about what thoughts those objects bring to mind. But in this case, we'll be doing with GeoGebra apps. So I'm happy that you're here. I'm happy that you've come out to watch this talk, and I hope you are sparked with creativity and joy. And if you do wind up watching this, please tweet out, drop me a message on Twitter, where it can be found at PG80. Okay, so I look forward to hearing any thoughts you might have coming out of this. But yeah, let's begin. So I'd like to tell you a little bit about geometry. This is in the context of a fourth-year mathematics course that I teach at the University of Toronto, Mississauga, but it can be done at any level. All of these activities can be brought down to the high school level, brought down to the public school level. It's really about meeting your students where they're at. So I'm going to talk a little bit about inquiry-based learning. The pedagogical framework that I come from is this inquiry-based learning, where students engage with meaningful mathematical tasks. So we mean meaningful here in sort of two senses. One, that it should mean something for the students. You know, they should understand what's going on. They should feel engaged with what's going on. And also, it should tie into the sort of the big ideas of mathematics, right? It should be meaningfully mathematical and should, have broader connections. So we want students to engage deeply with meaningful mathematical tasks. We want students to work collaboratively to process mathematical ideas. We want to work in groups and share. One of the things that I think about is really special about geometry is that we can kind of hold the objects in our hands. We can draw objects for each other. We can pass a mathematical object around and examine it from different angles, and we can create a kind of a knowing in a small group of people. So I think that working collaboratively is very important. We should focus on student thinking, right? We should see where students are at as teachers, right? This is sort of a key thing, but it's just important to remember that we should ask students what they believe about these things. Geometry is sort of special in that a lot of people have intuitions about geometry, and we can sort of point at things and say stuff. And this makes the conversation between instructors and students very fruitful and engaging. And then we should always foster equity, right? So when we're designing our courses, everyone has ideas about geometry, right? It's sort of a universal given that we can see pattern, we can see shape. So I think that there's a lot of room for fostering equity through this. And I'm going to talk a little bit about different mathematical approaches to doing that. So what's special about geometry? Right? Take a moment, sort of answer this for yourself. What do you think is special about geometry? And then I'll share a couple of my thoughts. Right, so sort of to reiterate those points, what's special about geometry? We can make meaningful mathematical tasks about pictures, things that are very in front of us, very accessible. Students can share their own mathematical thoughts because we have a lot of sort of mathematical intuitions. The conversations around geometry often wind up being very fruitful, and we're going to talk a little bit about this equity piece as well. So those are some thoughts about why geometry is particularly special. I want to share one thing that gives you the feel of what I think about geometry. I think the geometry is going on right here. Take a moment and kind of look at the different shapes, different things that you're seeing in this picture. Look at different ways that people are engaging in this picture. I always like to draw people's attention over to this corner of the picture, where we've got a student volunteer here who's really focusing on this child, right? The child is absolutely absorbed in their coloring task. This coloring task I'll talk a little bit about later on in the presentation, but we can see that there's some kind of a mathematical experience going on here. Another assembling some blocks. They're trying to make their own pattern. And then we've got all of these mathematical, tangible objects. People are holding these things, thinking about them, are a little bit excited. They've got all these fun, colorful things. And I think that this is one of the most exciting things about geometry. It's tangible, it's playful, and it's often colorful, right? It sort of has some properties that are usual mathematical subjects sort of lack, right? We sort of lack these tangible objects. So I think this is sort of a very special thing that geometry can do for us. Now I want to talk about where geometry is at in the curriculum. Right, geometry has been sort of relegated to the flanks of the curriculum. It's sort of looked down upon as kind of being 19th century stuff. Actual Euclidean geometry, we don't see very much of it. We talk about classifications of different shapes. We do some sort of 2-column proofs, but there's so much more to geometry than this kind of dusty old picture would suggest. And I want to come back and talk about why this specific thing would be very interesting to play with students, and talk about some of the ways that we play with it in our class. Just as a bit of a sort of historical aside, this model was made in 1864, came to Brown University in 1973, and that's sort of when it left the university scene. It's been sitting in the Smithsonian ever since. So this was a model built to demonstrate a particular concept in geometry, and since that fell out of the curriculum, it hasn't seen the light of day. Okay. So I want to show you what we can do with that in modern times, what that looks like these days. Okay, so I'm going to go over to screen sharing. You get this lovely fractal pattern. But the object that I was describing moments ago is what's called a Poisselier-Lipkin linkage. And if we were in the same space, I would hand you a physical copy of these. I have a 3D printed model of one, and I want to show you what it does. So when we move this point here, what do you observe going on when you see this thing move? Or you might not start moving that point. You might start moving this red point. Right, so what do we see happening here? Right, we see sort of some kind of relationship between two fundamental shapes, this circle and this line. And it's very mysterious why this is happening. What do the red bars have to do with this? What do the yellow bars have to do with this? Right. This was this linkage was sort of a mathematical construct, but it had physical applications. So in the 1800s, it was a major question in mechanics, how to convert circular motion into linear motion. To take a driving pistol at this red point and convert it into a circular motion for a wheel or something at this blue point. Okay, so this was open. People weren't sure how to solve this this sort of geometry problem. Watt, the inventor of steam engines, worked on it and wasn't able to come up with a solution. He was able to convert circular motion into elliptical motion, right? So if you move the blue point, you get an ellipse at the red point. But it took a Russian graduate student, Lipkin, and a French mathematician, Poisselier, to invent this linkage. So usually in a classroom, I'd bring in a physical model of this, and we'd play around. And what's interesting about this is that our geometry doesn't get us ready to describe what's going on. I've taken this model to a math seminar of undergraduates and asked them to try and explain what's going on. And about 2 hours later, we fill up a couple chalkboards, and we still have no idea. So we really need some classical Euclidean geometry to handle this thing. Giving this talk online now, we can actually play with the model at a sort of a deeper level, which is, I think, very interesting. We can adjust the radii of these things. So we can move the yellow bars. So what happens if we make the yellow bars very big, right? Right? How does the geometry change now? Right? What do we notice? We can change these relative lengths. We can increase the red lengths as well. Right? So one advantage to doing this in GeoGebra instead of a physical model is that we have a fair bit more control. We can play around with the various parts of the mechanism and see how that affects our geometric outcomes. Right, so one question that this naturally provokes is how much of the blue circle can we get? Right, how big can that blue circle get? And what would the relationship between that blue circle and that red line be as we kept varying things? Okay, so I want to go back to our slides. Okay, and we can see that this Poisselier-Lipkin linkage is much more alive and animated than this old model in the Smithsonian gives us, right? So there's lots to explore with this. There's rich mathematical tasks that could come out of playing with this mechanism, and bringing in a physical copy of these is one thing we can do. We can also bring in a virtual copy. And the virtual copy is a little bit more flexible in that we can adjust various bars, various lengths. Okay. Another object that's very, very satisfying to play with, and this is a task that you can do with any grade, all the way from public to post-secondary, is you can play with kaleidoscopes. There's lots to explore with regards to kaleidoscopes. They're very, very, very engaging, and they get us thinking about symmetry, they get us thinking about geometry, they get us thinking about transformations. So this is a physical kaleidoscope, and I've often given the talk where we pass around a kaleidoscope, various people look at it, then we classify all of the kaleidoscopes in the plane. We sort of prove a theorem that says what kaleidoscopes can exist. We talk about the geometry and symmetry of the kaleidoscope, and then we hand the kaleidoscopes around again and look at them again with fresh eyes. When we look at things with fresh eyes and a little bit more mathematical sophistication, we can often see a lot more of what's going on. So to take an example, we see that this has this beautiful pattern, but we need to investigate, what are these angles here? Right? When we prove the classification theorem, we get talking about what these angles are. What triangle do we really have in this region? And right, does this triangle seem familiar to us? What can we deduce about those angles? It turns out that this is a 30, 60, 90 triangle, one of the special triangles. We can see that if we look here, if we look at it in its mirror copy, right, when we look the first mirror copy of that triangle, we see that we've got an equilateral triangle, right? So this angle here has to be this angle here. And then that gives us that this has to be the same as well, right? We've got a 60, 60, 60 triangle. Okay, so there's lots to see and vision in kaleidoscopes. Going into our virtual environment now. Right, we can do the same kind of thing online virtually. Right, we can play with kaleidoscopes and see what happens. Right, how do those symmetries repeat when we go into a reflection, right? So notice that these purple swirls, right, they get copied into all 6 congruent regions. And one thing I like about this particular app is that every even reflection is colored the same way, right? So the first reflection is colored gray, the second reflection is colored purple, the third reflection is colored gray, the fourth is colored purple, the fifth is colored gray, the sixth is colored purple, and so on. Okay, this is quite nice. Okay, we can play around with different amounts of symmetry. Right, so again, the virtual model gives us a little bit more flexibility than the physical model. Right, we can have 4-fold symmetry. We can have 8-fold symmetry. Right, so there's a lot we can do with these symmetric regions, and I encourage you to play around with these a little bit. When we're back in physical settings, I highly encourage you to get a pair of mirrors and bring those to class and experiment with showing your students how the image changes as you vary the angle between the mirrors. Okay, so kaleidoscopes are a physical object that we can bring in. We can ask students to inquire into them. There's all sorts of connections throughout the curriculum, and I find that we can really see them with new mathematical eyes when we ask students to investigate them and then do some kind of math surrounding the geometry and symmetry, and then look through them again. The experience of sort of leveling up and noticing that, say, that equilateral triangle is often very powerful for students. Okay. This is a piece of art by Escher, very famous artist, not a mathematician, but very, very deeply aware of the significance and power of mathematics. And what I love about this painting is that it suggests something, but it is not clear what. Right? We see this and we say, okay, there is some kind of pattern here. I feel that there is some kind of structure here, but I don't know what structure it is. And that's a really powerful moment for our students. Right? We look at it, we can inquire, we can ask questions, and it's not clear what the answers to those questions are. There's some kind of structure. I don't know what it is, but I wish I did. So, some things that you can point out. Notice here we've got a point of fourfold symmetry. Right? We've got a cross there, and we can rotate. If we ignore colors, we can rotate 90 degrees about that center. If we care about colors, we can rotate 180 degrees about that center. Over here, we've got a threefold reflection point, a threefold rotation point, but it's not a rotation point of the whole picture. Right? But this turns us on to the notion that there are squares and there are triangles. Right? Here we've got the outline of a square. And then here we've got the outline of a triangle. And then a square. And then a triangle. Right, and this pattern repeats all the way out to the boundary of the region. We can talk about particular colors come together. Right here we've got brown and yellow. Here we've got another point with brown and yellow. Here we've got another point with brown and yellow. And all the way out to the boundary again. So there's lots of patterns that we can look for in this painting, lithograph. And the more we look for them, the more we find them. This painting was famously commented on by the Canadian geometer Donald Coxeter, who initially, when he saw it, thought, "Oh, this is sort of a cute thing, sort of a mathematical mistake somehow, but we'll let it fly." And he didn't think much of the mathematics of it. And then about 10 years later, he looked at it again and he saw that some of his research was actually embedded in this painting, and he didn't even know. He noticed that there was a uniform tiling of the hyperbolic plane that he had discovered that was evidenced in this, and that Escher didn't know that he had created. So there's mathematics to be discovered at a very high level inside this. The sort of closest connection to contemporary mathematics, kind of the deepest connection, would be to the notion of hyperbolic geometry. Which we can explore, again, using software. We can use software to investigate sort of these hyperbolic structures. Right, so looking at this, we see that there are these sort of straight lines, and there are these curved lines. And in a hyperbolic geometry sense, these are in fact all straight lines in the hyperbolic metric. Okay, from the perspective of those fish in Escher's work, the line AB, right, this curved line here, AB, is just as straight as the line EC. Okay, so from a hyperbolic perspective, circles become straight lines. And we can talk about what properties circles have that are in common with straight lines, both in the Euclidean context and in the hyperbolic context. So this is something where a computer visualization can really show us a lot. Right? How do these things morph? Right? We had just said that EEC is a straight line. but now suddenly it's become a circle. But as we move back towards the center of the disk, EC becomes a straight line again. So there's a lot to explore. There's lots of questions that can be asked here. And having a conversation about what's going on in this demonstration would give us a lot of insight into what's happening in those the universe where those fish live. Okay, so the universe of these fish is governed not by our usual Euclidean notions of straight, but rather by a hyperbolic geometry notion of straight, where circles can become straight lines and straight lines can become circles. So there's lots of mathematics to investigate there, and I think that with a famous piece of art like this, we have an opportunity to have something that's both aesthetically satisfying and mathematically satisfying. So a very, very deep source of conversation. To bring this back to the equity piece, here's another piece by Escher, and this is modeled on a piece of art that he found in the Alhambra. And this is something that can be constructed with ruler and compass. This is straight Euclidean geometry. But it's also a place to talk about culture and mathematics and the role that mathematics can play in culture. Much Islamic art is geometric, and we can talk about why that culture has evolved art in that way, and what insight geometry can give us into art from different cultures and the beliefs of different cultures. I think this is a very, very satisfying piece. There's lots to look at in it to try and hunt down where there are straight lines that connect up different parts of the diagram. Right? Or how many sides does this thing have? Or, what kinds of symmetry does this have? Does this have a fourfold rotational symmetry? Right? What parts of the diagram move when we look at the symmetries of this object? And how many of these black regions are there? And what angle must be between them? What are these little angles here? Right? Is this small yellow angle the same as the angle at the center? If we were to start at the center and go out to the tips of those regions, would we have the same angle? So one can produce photocopies of this diagram and go about investigating these things with rulers and protractors, and engage with some classical Islamic art. And there's also constructions that you can do based off this. So you can get your compass and protractor and ruler and build out some of these things as a geometry lesson. There's lots and lots and lots of resources on teaching geometry with inquiry. I highly encourage you to look up these resources. All of them have activities that could be used in the public school setting, the high school setting. There's lots and lots of things to explore in geometry, and it can be explored at many different levels. Okay, so I want to close off this this presentation just with a reminder that students come first. There's many things that we can do with students to help them explore geometry, to find their way into geometry. It's a satisfying exercise to both notice how happy these people are, how much is going on, and how many geometric objects there are on the table. Where can you find geometry on this table? So thank you for taking the time to listen to this presentation. If you have any comments or questions about the presentation, I encourage you to reach out on Twitter or by email. I'd be happy to talk with you about geometry, mathematics for the eyes and hands, and hopefully in the future, going forward, to share some models with you and to share some exploration. Thank you very much. I hope you enjoy the rest of OAME. It's been a pleasure.